Namaskara. We will continue our discussions on the algorithms for minimum spanning tree based on the greedy approach. We will first make a quick recap of what we have done so far so that it sets the tone for our further discussions. You are given a graph G which has got a vertex set V, edge set E, and there is a weight function. Weight function associates for each edge a weight which is a real number. Now we consider as integer, and let L be the list of edges in increasing order of their weights. Now the spanning tree T is denoted by the same vertex set and the edge set is A, and our algorithm is as follows. Initially A is empty while not and E equal to first edge of L, while not end of L. Okay. If E does not form a cycle with edges in A, then we are going to add, then A equal to A union E. If E forms a cycle, then we ignore that. If it does not form, we include. So either we include or ignore and then proceed for the next edge. E equal to next edge in the list. So this we do while not end of L, and then we are going to return T, which is vertex set V and edge set A. This is the algorithm. So think for a moment how we can determine whether an edge E is forming a cycle with some of the edges that we have already collected, just as a thought experiment with no data structure, with no specific plans in a graph. Suppose you have collected about 325 edges, and now there is a new edge. There are 325 edges in A and there is a new edge. Now you have to figure out whether it forms a cycle with some of those edges or not. It is really complicated computationally thinking about a process. Therefore, we are looking for certain equivalent ways and properties which are helpful for us in coming up with a computational process. So we look for the characterization. We actually do not want the cycle. We want to know whether it forms a cycle or not. So the one characterization is E equal to UV forms a cycle if and only if there is a path connecting path, let us say from U to V using edges in A, which is same as this is if and only if the vertices U and V belong to same connected component of A. If U and V are in the same connected component of A, then there is a path. If they are in different connected components of A, then there is no path. So I can very clearly say when it is going to form a cycle, when it is not going to form a cycle. Just look at the end vertices. Okay. All I have to know is a mechanism to identify. So I need a mechanism to refer, label the connected components, and then given a vertex we have to report which connected component it is in. So, I find a connected component containing U, connected component containing V. Are they same or different? So, when I answer that question, I will be answering the question whether E is going to form a cycle or not. Therefore, we have formulated the problem into an equivalent setup in the partition induced by the vertex set, partition of the vertex set induced by the connected component, whether they are in the same set or not. So, we have introduced the partition ADT, and in the partition ADT we have introduced two operations, union and find. Union takes two different sets and creates the union of it. Find returns the name of the set containing the vertex. With this, armed with this, okay, assuming that abstract data type is available, I can write the following. A equal to empty is same as there are no edges, therefore the initial partition is isolated vertices. When you have the isolated vertices, then the finest partition, singleton element, n singleton elements, that becomes your starting point, and then you follow the same procedure in the following way. So, L is the list, T equal to VA, A is empty, E is the first edge, and initialize the partition. That depends on the way in which we will. So, initialize the partition again while not end of L. Okay. So, let E equal to UV, X equal to find U. This returns the name of the partition, X is the name of the partition containing U, Y is find V, Y is the name of the partition or the set containing. If they are same, then this edge is to be ignored. If they are not same, then right, they do not form a cycle. If they are same, they form a cycle because they are connected. So, E does not form a cycle is translated into if X not equal to Y. You can see how this condition is so nicely translated into if X is not equal to Y, A equal to A union E included. When you add E, the partition changes because the edge E, which is having their end vertices in two different connected components, they become a single component, right. They are, therefore, we have to perform the union. So, union X Y. If X is not equal to Y, A is updated and the connected component information related to new A is also updated by performing the union operation. The difference between the connected component information of old A and the new A is the presence of the edge takes the union. I can give a simple picture here. This is the name of the set X, this is U, this is the name of the set Y, this is V, this is the edge. So, now the connected component is X union Y. That is what is done here. So, if you see what is done here is that I have updated A and okay, and then E equal to next E L, and this is what the while loop, and then return V A. Same code. So, you can see how our mathematical description is converted into a programmable entity via the concept of abstract data type and the operations done on the abstract data type and matching of that with the graph theoretic concepts that we wanted to implement and so on. And this makes the complexity analysis a lot easier. That is because we have got a name array implementation, name of u equal to x means x is the name of the set or component containing u. With this interpretation, we have introduced a data structure that has got union of, let us say, x, y, it costs order n, find of any cos order 1. With this complexity figure, you see that the find operations here take order 1, the union operation here takes order n, and for each edge you are doing 2 find operations, therefore the cost will be 2m, and there will be n minus 1 union operation. For each edge of the spanning tree you will perform 1 union operation, and any spanning tree is going to have only n minus 1 edges, therefore those n minus 1 times n, and therefore this becomes order m plus n square algorithm. It is a very nice algorithm, and it is a very nice implementation of Kruskal's algorithm. We are using a data structure called name array and implement partition ADT, and via partition ADT we implement a graph algorithm of finding the minimum spanning tree. You can see how finely various threads of algorithmic thinking, computational thinking, mathematical thinking, and putting them in terms of a data structure and abstract data type, lot of things have come together in this case study. And once I have the partition ADT as a key tool for implementation, I can look for a completely different way in which the partition ADT can be implemented, and I can plug that in here. As you can see, this algorithm, how you have implemented find and union does not matter, right? This code will work. So, I am now going to come up with a completely different implementation of the partition ADT, okay, a totally different way of implementing it with a completely different characteristic, complexity figures and so on. Okay. So, this is called modular design. Okay. It is also known as procedural abstraction. We are distinguishing what is to be done from how it is done. First of all, determine what is to be done. Then you go about worrying on the implementation detail, how we would implement it. Okay. So, this modular design is extremely useful in software design and program design and implementations, computer based implementations, because we will be able to replace individual parts, okay, without changing anything globally, okay, or we can use reusable component. There are several interesting software engineering principles and ideas which you can understand through this very interesting case study. So, my main code will remain same, but I am going to change the implementation, Okay, it's almost like you. Let's say you have a car and you have to change your tire. You have several options. You can buy Seat tire or MRF tire, or there are several. Anything you can fit. Okay, each one has got its own characteristic. That's because it is a modular design. You don't have to change the entire wheel assembly. It's enough if you change just the tire. Okay, so that's because of the modular design. They are independent, and we have the separation of the modules. So each module can be independently worked on and improved, and can be used. Okay, so we will now take a look at another implementation of partition ADT. So partition ADT has got an underlying universal set. We assume that that universal set is 1 to n, and a K partition will have K sets S1, S2, etc., Sk. This is the K partition, and we need an identifier because we have to refer them in order to access, use, and so on. So name of a set or identifier of a set is the minimum number in that set. In fact, you can use any number in that set because each number will be in exactly one set. All right, we can, in fact, this flexibility we will use later. In fact, we may use any element of the set as its name, because name should be unique and an element belongs to only one set. It is a partition, it is not in several sets, and every element is in some set or other. Therefore, there is no ambiguity in choosing an arbitrary element of a set to serve as its name. Okay, it is an identifier. It is uniquely identify the object. So name of a set is the okay. And now we will use a completely different representation for the partition. This is called inverted forest representation. Inverted forest consists of several inverted trees. Okay, several inverted trees. These trees are rooted trees. All trees in computer science are rooted trees. They are directed rooted trees. By inverted, what we mean is that all edges are directed towards the root. All edges are directed towards the root. Okay, so you can have something like this. All edges are directed towards the root. So from any node you can keep going to its parent and parent to parent and so on, and you can reach the root. Okay, that means an edge is between you and parent of you. Every edge connects. Every edge connects you with its parent. Sorry, there is a I will rewrite with its parent in the tree. So, every node is referring to another node which is its parent. There is an exception for the root. Root does not have a parent. Therefore, at root we provide a self loop. We attach a self loop at the root. This is a distinguishing property of a root. Therefore, parent of root is root itself. Okay? Parent of root is the same one, because it is a self loop. It is referring to, so through parent we are referring to a node. So, parent, the P can be viewed as a pointer. For our purposes, P will be simply an array. Okay? It is a parent array, you can call that as, because it will have the index or the value which is in the parent node. Very simple representation. Pictorially, this is going to be like this. The trees can have arbitrary shape, there is no restriction. Okay? A node can have several children, and the shape, size, absolutely no restriction. So, 1, no restriction or condition on the shape of the tree. We will place the name at the root. Okay? Place the or store the name of the set at the root. Three, one tree per one set. Each set will be represented by a tree, okay, and one value, one element of a set per node. So, each node will have one element of the set and one tree per set. That is the reason why if there is a k partition, there will be k trees. Okay? That is why it is called a forest. What is a forest? It is a collection of trees. Forest is a collection of trees. So, a k partition will be represented by a set of k trees. Each tree will represent a particular set, and the name of the set will be at the root, and so on. So, here is an example. Okay, let us consider the partition for 12. 1, 2, 7, okay, 3, 5, 4, 6, 9, 11, 8, 10, 12. Let us say we have 13 also, a singleton 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, all elements are here. This is a partition of 13. So, we can represent this in the following way. Currently, we will follow the convention that the minimum is serving as the name of the set. Therefore, you are going to put minimum in the root, all other elements anywhere. There is no restriction on the shape or the way in which the values are assigned. For example, I can use the following tree to represent the so this is 2, this is 7, and this is 1, here I have a self loop. 3 and 5, I will put 3 here and 5 here. 3 is the root. Here 4 is the name, that will be in the root. 6, 9 and 11 can be in any manner. This may be 9, this may be 11, and this may be 6. You can see I am allocating one value per node, and for each set there is a tree, and the name is placed at the root. The root is distinguished node. Only root has got self loop. All others have got their parent referring to some other node. Okay. And 8 and 12, the name is 8. This 12 may refer to it, and 10 may refer to this. And 13 is singleton, that is the root end. So, this is the forest representation of the partition. Okay? Inverted forest representation of a partition. How do I implement it? I will use a single integer array, that is good enough, called the parent array. Parent of 1 is 1, because 1 is referring to it. Parent of 2 is 1. Look where 2 is taking 2, it is taking to 1, its parent is 1. Parent of 3 is 3, parent of 4 is 4, and parent of 5 is 3, parent of 5 is 3, parent of 6, where is 6? Parent of 6 is 11, parent of 6 is 11, and parent of 7 is 1, parent of 8 is 8, parent of 9 is 4, parent of 10 is 12, parent of 11 is 4, parent of 12 is 8, parent of 13 is 13. That is it. You can see that it is a single array. One array represents the entire collection, whatever is the number of sets. You may have n may be 5000 and you may have 400 sets, does not matter. A single array represents all, the entire collection, such a beautiful representation. So, here all the conceptual things that we had about inverted forest, everything is hidden. If you simply look at P, it is an integer array. Okay? So, the inverted forest is completely hidden here. Okay? Such a data structure is called implicit data structure. The word implicit means hidden, it is understood, it is implicit. Okay? P is simply an array, but what is understood and what is hidden here is actually a forest. The entire forest is hidden in a single array. All right. Now, in this representation, how do you do union? You are given the sets, you will be given the names of the set. Find the union of these two sets, those two, the reference or the names will be given. Okay? So, how do you perform the union? If you look at this picture, okay, and the convention that we have, let me copy this picture down, because I need let us say 3 and you have 3 and 5 and you have 4, 9, 11, 6. 9, 11 and 6. These are the two sets. I have pulled out from the example and I have written it here. How do you perform union, let us say 3, 4? Union 3, 4 if I want. Two sets and their names are given, you have to do. The union is performed in a very simple manner and it is called tree hooking. You hook one tree to another, you attach one tree to another and make one big tree, right. So, we know that the root should carry the name. By our convention, minimum is the name. Therefore, you are going to hook the tree with 4 as a root to 3. So, what you are going to do is, you are going to simply do the following. Instead this being a parent, now for parent, you do this, that is all. Now you see there is only one tree and 3 is at the root and this tree has got all the elements, union of all the elements, okay. So, in some abstract form you can see that if this is one tree, if this is another tree, earlier you would have got a self loop, but that self loop will be replaced by this. So, how do you do that? Earlier parent of 4 was 4 because there was a self loop, make that into 3. So, union of 3 and 4 is achieved by simply making parent of 4 equal to 3, that is it, only one step. In general, how do you do union of x and y? If x is less than y, hook y to x, parent of y equal to x, because this is the name of the new set and by hooking all the elements are put together in a single tree, okay, all the elements are put together in a single tree. So, let me give two different pictures so that it is like this. Let us say this is x and this is y. X union y you have to take, x is less than y, therefore, this is transferred to, this is x, this is y. Earlier there was a self loop at x and y, now parent of y is x. If x is less than y, parent of y equal to x, else parent of x equal to y, that is it. This is the code for union. X may have 1200 element, y may have 800 elements, does not matter. The union of these two sets is done in one step. Amazing. The complexity of union under this representation is order 1. In our earlier representation, we went through the entire array, wherever y was there, we would change to x. The name will be changed physically by going through the entire array. That is the reason why the complexity was order n. The entire array has to be scanned. Here, the tree hooking is done in this representation. The union can be done in one step, whatever is the size of the sets involved. So, this picture will clearly tell you how the union is done, okay. amazing operation and then the beautiful representation and extremely efficient performance of union. How do you do the find operation? The find operation should return the name of the set, find x, it should return the name of the set, but the name is at the root. So you should start from that vertex, go to the parent of parent of parent of, this is called ancestor chasing. By doing the ancestor chasing, you will reach the root, parent of and the parent of and so on. For example, what is find of 6? Parent of 6 is 11, parent of 11 is 4, parent of 4 is 3, parent of 3 is 3. That is the characteristic of the root. That is the characteristic of the root. The root, only root will have a self loop. The parent value is the same. For all others, parent will be different. It may be smaller or greater, that depends. For example, parent of 6 was larger, parent of 11 was smaller. It will be different. Because we didn't put any restriction, the relative values can be in any way, it does not matter. We are only interested in the cluster information. What are all the items that are in a set? And we place the name at the root. Therefore, by ancestor chasing, you are going to execute the find routine. Okay? Therefore, let us start from find x, right. So, if you want to do the find x, you start from x, alright, and then keep moving from there. So, there must be a value y that keeps moving along the ancestor. When that moving value reaches the root, you return that. Okay. So, here is the find x. This is the union procedure. This is the find procedure. Okay. So, find x, y equal to x. So, y is going to be used to chase through the ancestor, y equal to x, while y is not equal to parent of y. If y equal to parent of y, that means you have reached the root, right. While y is not equal to parent of y, move y up, y equal to parent of y. While y is not equal to parent of y, keep moving y up, y is updated to its parent. There you check its parent value. For example, if this is x, find 6, this is x, and initially y equal to x. Is y and parent of y same? No. Y is 6, parent of y is 11. Parent of y, which is parent of 6, is 11. Therefore, it is not same. You update y, you get into the while loop and y equal to parent of y. So, y is updated to this. Is y equal to parent of y? No, y is not equal to parent of y, because y is 11, parent of y is 4, they are not same. Get into the while loop, get into the while loop, y equal to parent of y, update y to its parent. Check whether y is equal to parent of y. No, y is 4, parent of y is 3, therefore, you are seeing that they are not same. Get into the while loop, y is parent of y, update y to the parent. Is y equal to parent of y? Yes, y is 3, parent of y is 3, they are same, So you exit the while loop. The while loop condition is violated. You are going to execute the while loop as long as y is not equal to parent of y. When y equal to parent of y, you have reached the root, you exit the while loop, and what do? Return y. That is it. This is the find routine. This is called ancestor chasing. You do the ancestor chasing and then reach the root and return the value of the root. That is the name of the set. So for every element, the find returns the name of the set containing that element. How does it do? By ancestor chasing. So what is the complexity of the find routine? The complexity of the find routine is the depth of x, because from x you keep going up and up. How many steps you will go? As many steps as x is down from the root. That is the depth of x. Whatever is the depth of the x, that many steps you would execute in the ancestor chasing, reach the root and then return the value. Therefore, the complexity, the worst case complexity of the find operation is depending on the height of the tree in which you are performing the find operation. The find operation is done in a particular tree. You are starting from a node and then you keep going up in the tree and reach the root of that particular tree. Whatever is the height of the tree will be the worst case complexity. Okay. Therefore, I have now a new data structure for partition, and here is the union find routines. Now you can see how do I initialize the what is the initial partition? Initial partition is 1, the finest partition, 2 n. This is represented by 1 at self loop, 2 at self loop and n at self loop. Each set, that is the set, and that's so this is P of 1 equal to 1, P of 2 equal to 2 and so on, and in general P of I equal to I is the way to initialize this partition. That is the way to initialize the partition, and then you can go ahead with your union find operation. Therefore, this algorithm, the algorithm that I have written here, you can see this algorithm works. You have a find routine, union routine, their implementation is available, the same code works, no change. Only thing is you have to initialize the parent array, initialize A, initialize E, initialize the parent array, the same code works. You can see that I have changed the data structure without changing the implementation. This is a beautiful way for the development of the code. Okay. I have an algorithmic logic, I have an implementation through abstract data type, and the implementation of the ADT in terms of different data structures I can plug in and plug out. Okay. For example, if you are using in an application a sorting algorithm, okay. Currently let us say you are using a very inefficient sorting algorithm because you are not aware of some. Later on you came to know that there is a better sorting algorithm available, then you can simply pull out just that part alone and replace it with your more efficient one, and that is possible if your design is modular. Okay. This abstract data type or procedural abstraction allows us to do such things. Okay. That is illustrated beautifully in this. Now I have discussed a completely different data structure representation. The same code works, high level code works. Internal details of course are different. The union routine in the name array is different from the union routine in inverted forest representation. Here you are doing tree hooking, there you are scanning the entire array. So, the implementation details will be different, but the advantage we have is that at a higher level we have an implementation detail frozen through abstract data type. Okay. So, that is important lesson that we pick up from this case study. Okay. So, the union is order 1 in this, union is order 1, find is order of the maximum height of a tree in the forest. We are going to see this could be order n. In other words, find may have a complexity order n. We will see the examples and other related discussions in our next session. Thank you.